This is a video on computational fluid dynamics for gas scrubber design. Now, CFD, computational fluid dynamics, is a method for modelling complex fluid flows. CFD can be used to model where sprays will end up going in a particular gas flow. And as such, they can be used for helping optimize gas scrubbing applications. Now, a lot goes on in a gas scrubber. It gets complicated. We have literally tens or hundreds of millions of individual drops of varying sizes moving around. And it's often complex and turbulent gas flows. It's a complicated system. Very simple spray trajectory plots, which we can get from simple software, into simple uniform gas flows at constant speeds are okay for kind of testing very basic assumptions, but they won't truly model what's going to happen in the real world. Now, for many scrubber designs, we can use these very basic assumptions and then throw a bit of extra liquid at the problem to ensure that it's going to work. We can look at the very worst case assumptions and design the scrubber to cope with those worst cases. Whilst this worst case approach is widespread, common, it's clear that it will not produce the most optimum of results, optimum of scrubber designs. It's not actually practical to run real life tests for most scrubbers. They're expensive, and by their very nature, they're hot and full of lots of pollutants. So building working models and then to test how they perform with different spray scenarios is hardly practical. So CFD is a way we can test scrubber efficiency without building an actual scrubber. So kind of halfway out between having a live working model or using very sort of basic assumptions and worst case scenario assumptions. This is a way that we can actually improve scrubber design and optimization. And the way this is done is to select a range of spray nozzle candidates and measure their important drop sizes in the lab. Now, in the previous video, we talked about the different drop sizes that are important. These will be the DV09 to measure the heavy droplets, the DV01 to measure the fine droplets, and the DV32, the sort of mean, which is a measure of the average drop sizes or surface area. We can test all of these in a lab with different nozzles that we're considering. We can test them at different pressures, and this will form our raw input data. It builds up a picture of the sprays from various different nozzle scenarios, and we can then input this data into our computational fluid dynamics, along with the gas flow data and the geometry of the scrubbing chamber. We put all of that data in, and then we can start to model what's actually going to go on. The problem with the modeling of data of this nature is that CFD is not simple. It takes a lot of computing power, and we also need that initial lab data to act as an input into the CFD calculations. Now, this is no mean feat in itself. We need a proper spray lab that understands the subtleties of drop size measurement techniques, and this is an absolute must. As the saying goes, if you put garbage in, you get garbage out. So if you don't have the good spray lab data going into your initial CFD calculations, you're going to get poor results out of it. Having a proper spray lab that can measure those drop sizes and understands how to do that properly is absolutely vital input for any CFD calculations. Once that's all input, we can start to model what the spray is actually going to do. We can then start to calculate absorption rates, we can calculate mass transfer, heat exchange within the gas, and we can test a number of different spray setups with perhaps different nozzles or different feed pressures, and now we can start to build up a picture of what's going to be the optimal scrubber design. The good news is that through our core nozzle supplier, a Beat Fog nozzle in the US, we have access to all the required spray labs and CFD capabilities. Now, because Beat is one of the world's leading spray nozzle manufacturers, you can rest assured that those vital inputs into the CFD, the measuring of the drop sizes, the testing of the different sprays, is going to be correct. And so it's going to produce useful and reliable models. Now, the cost of CFD has come down quite considerably in recent years because it is primarily driven by computing power. It takes a lot of computing power to do CFD, and as computing costs decrease, so does the cost of CFD. However, it's still not a cheap process. We still have to do that initial lab work, that initial empirical testing of different spray setups, and then we've still got some fairly hefty computing to do with specialist technicians to understand how to use the CFD programs to get the results out of it. So whilst CFD isn't going to be used for every single basic scrubber design, it is coming down in cost, and it is starting to help us optimize and improve scrubber designs as we go forward. And that's probably going to become more and more the norm as the cost of this technology actually comes down. For scrubber design, this is actually really, really good news, because if we can optimize scrubbers, we can make them more efficient, we can reduce pollution more, and help save the planet, which is obviously good news for everybody. CFD is something we're fully capable of deploying in scrubber design. We're qualified to do it. We have the partners in place to do the initial lab work and testing. And so if it's something of interest, if you're looking to optimize those scrubber designs, then we're a good company to come to start talking about how we can deploy CFD technology to optimize your scrubbers.